Alright, this is the 2014 Physics Regents exam. I'm using this as a review, and I'm only going to be doing the problems leading through the first, half of the year. We're going all the way through mechanics, which takes us through all the way to momentum. Our next unit that we'll be covering is static electricity, for anyone else that's watching. So I basically went through and I put the questions on the left side, and I put what the answer booklet itself looked like for this particular test on the right side. I'm going to try to kind of simulate taking the exam and go through the point breakdown. You're going to see some stuff that is not anything I'm covering here. I'm just going to ignore it or cross it out. So for this first one, the information up top is provided, and we have a 60 Newton force, which is east, and an 80 Newton force, which is north, acting concurrently on an object at point P. And we need to use a ruler to determine the scale of the diagram. Now, I'm not going to take a ruler and measure it because I know it's not accurate. It's not to scale. I shrunk this whole diagram up. So what I encourage you to do is actually practice this. Take a ruler, measure how many centimeters long either of these two vectors are. It doesn't matter which one you measure because they're going to be the same scale at least. So you're going to measure how many centimeters each vector is, and then divide by the actual force that's listed. And it turns out that every 1 centimeter is 10 newtons. So in this particular question, the 80 Newton vector would have been 8 centimeters long because every 1 centimeter represented 10 newtons. Now, because there's some degree of error there, the answer key gives a little bit of room. So the preferred answer is 10, but you'd get away with saying anywhere from 9 to 11 newtons. And that's going to get you 1 point. I'm going to label the points you get for each one off on the side here. For 52, we want to draw the resulting vector to scale in the diagram. We're going to label this R. Now, despite practicing these millions of times, I see a lot of students just try to complete what they think is the right triangle. They try to draw the hypotenuse, but that's not correct. Please don't do that. Really encourage you to kind of think it through for a minute first. If there's a force pulling an object north and another force pulling an object east, it doesn't make sense that you think it'll go southeast. It's got to go a combination of the two, and ends up going northeast. So the easiest way for me to describe how to do these problems is I always encourage you to redraw one of these vectors because I like to do these in the tail-to-tip method. If you look at it, both the north and the east vectors tails start together, and that doesn't follow the tail-to-tip net method. So what you should do is draw one of them over again. So for that, I'm just going to trace it. I can just slide it up here. You got to use a ruler. Make sure you do it properly. Now you'll see that this northward vector's tip is aligned with the eastward vector's tail. And your resulting vector is that final vector that starts at the tail of the first and finishes at the tip of the last. And it's that red one I just drew. Now that is the resulting vector. It's the northeast vector that comes from the north and east vectors. We got to label this one R. This one was worth 1 point. You basically, again, you were allowed a little bit of leeway because you were using measuring tools. So, you get a plus or minus in here. You did get credit if it's labeled. If it's not labeled, but you did not get credit if you're missing the arrowhead because that doesn't give you your directional information. So make sure that arrowhead is there. For number 53, we want to determine the magnitude of this force. Well, there are two ways of doing this. The goal, I think, for this problem was to use the ruler because they gave you the scale. So that's the easiest way, is to actually take your ruler, measure how long this is in centimeters, then multiply that number by 10 because each centimeter represents a newton. This particular vector ended up only being about 10 centimeters long. So it ends up being a 100 Newton force. Now you could have done Pythagorean theorem. It wouldn't have been a problem because it didn't say explicitly you had to use a ruler. But I'm not going to go through for this problem. And then number 54, we want to know the angle between the north and the resulting vector. It's important to really make sure you're reading that properly. We're looking at the angle between the north and the resulting vector, which is this angle up here, not the resulting vector and the 60 Newton vector. For that, they wanted you to place the protractor. Again, you could have done trigonometry to figure this out, but I'm going to go ahead and assume that you were using a protractor. If you lay down that protractor properly, you'll see that this is a 37-degree angle. And you will get a plus or minus 2 degrees for that answer. So 53 was worth 1 point, and 54 was worth 1 point. So this 4 set, they're each worth 1 point, as you can see here. You know what, maybe I'll stop labeling the points off to the right. I'll just show you how each point is awarded if it's worth more than 1 point. Yeah, that's what I'm going to do. Alright, so I'm going to turn the page here. 55 through 56 go together. We have a 3 Newton force causing a spring to attach, to stretch 60 centimeters, and we want another spring constant for the spring. That 3 Newton force is going to pull that spring down. Now, you don't need to show this part that I'm showing, but you do need to show work for this. It says show all work including equation substitution with units. That's how you get both your points. But this portion you don't need to show. I'm just going to kind of illustrate here that we have this spring that's been stretched a certain distance, and it's supporting this object of 3 Newton forces. So the whole distance it's stretched is the distance away from its original equilibrium position. And so that's what we're going to call our x value for this spring analysis. If I can get rid of this box. It drives me nuts sometimes. There we go. And so recognize that because that object is being supported by the spring, the object has its weight down, which must equal the force the spring is pulling up. Therefore, the spring force must equal the weight, which you may recall is also, the spring force is also equal to kx. This is Hooke's law. We're looking for k, so k is the weight divided by x. And that weight was given. Don't go ahead and multiply by g again. It's already in newtons. So we have 3 newtons divided by 60 centimeters. Now, you don't actually have to convert out of centimeters so long as you give your final units properly. But I'm going to convert that 60 centimeters to 0.6 meters. Remember, move the decimal place 2 to the left. And you're going to get an answer of 5, and the units would be a Newton per meter. If you left it in centimeters, oops, I'm saying centimeters when I want to write meters. So it's 5 newtons per meter. If you left it in centimeters, you would have gotten an answer of 0.05 newtons per centimeter. So as long as you illustrated your units fine, you'd get both points. So basically, you get the 1 point for the right answer, and you get the other point for showing your work, showing your substitution with units, and getting your units correct on that answer. Now, remember, you can make a knowns list, so you don't need to plug the units in directly as long as you make a knowns list. But you still need to substitute. Okay, we have for number 57, we have a 7.28 kilogram ball traveling 8.5 meters per second east. Let's get a hit head on with a 5.45 kilogram bowling ball traveling 10 meters per second west. We want to know the magnitude of the total momentum of the two-ball system after the collision. Notice you don't need to show work for 57. They don't even give you a lot of space. You're supposed to kind of do your work on a scrap. All they're looking for here is the correct answer. So I'm going to show my work down this weight space down below here. Again, you didn't have to do that. And we want to know the total momentum of the two-ball system after the collision. First and foremost, remember, momentum is always conserved in collisions. So the P before needs to equal the P after. Now we're looking for the momentum after the collision, but they didn't give us any information dealing with afterwards. They only gave us the information dealing with prior. So that's what we're really going to find is our momentum beforehand, and that will equal the answer that we're looking for. So the momentum beforehand will be the mass of the first object. So I was going to say ball, but they're both. So I'm going to say, let me erase this. I'm going to say MAVA and MBVB. So I have MAVA plus MBVB must equal the answer I'm looking for, the momentum after. I'm going to go ahead and make a little knowns list so I don't have to sub my units in because it's going to be kind of annoying with all those letters and numbers. So I'm going to say the mass of object A is 7.28 kilograms. The velocity of object A is 8.5 meters per second. That's east, so it's positive. Object B is 5.45 kilograms. And velocity b is west, so it's going to be negative 10 meters per second. I got to be careful to carry that negative over when I plug it in. So now my final answer, p after, will equal 7.28. Oops. Okay, I'm just going to erase that. It's 7.28 times the velocity, 8.5, plus 5.45 times negative 10. Don't forget the negative. Anyhow, we're going to get ourselves a value equal to 7.4 kilogram meters per second. Fortunately, we don't need to worry about units or anything here, because all we got to do is write in 7.4 into the box. For this actual one, I accepted 7.4 or 7.3, I think, due to rounding issues. So you could have actually had 7.3 and gotten it correct here. I'm going to get rid of all of this stuff, all this work we don't need anymore. Okay, 58 through 59 would be this one up here. We're going to be dealing with power, so we want to know the average power required to lift a 490 Newton object a vertical distance of 2 meters in 10 seconds. We do need to show our work, so I'm going to make a knowns list and indicate that the power is equal to 490 newtons. I know the distance it is lifted is 2 meters. I know the time to do that is 10 seconds. Looking at my reference tables, I see that the equation for power is work over time. Now, I don't have... Ooh, look at that. I'm silly here. I made a bad knowns list. This isn't power. This is force. Look at me, it's newtons, and even says force. Anyhow, power is my unknown. Power is work over time, but I don't directly have the work, but I do know that work is force times distance. Therefore, I'm looking for power is really going to be force times distance over time, which is simply 490 times 2 divided by 10. And remember, since I've already put a knowns list, I don't actually need to go and put in my units until the end, of course, and I get an answer of 98 watts. 2-pointer, once again, you're going to get that 1 point for the right answer, and the second point for clearly showing your work and all that good fun stuff. Alright, 60 and 61 are curriculum that we haven't covered yet, so I'm not going to do those. We'll move on. We're looking at 63 through 65, and we can do that. And so, 63, well, it's really this velocity time graph for both of these. And you have a car moving in a straight line, and we have a velocity time graph going. For 63, we want to know the magnitude of the average velocity of the car. It's only a 1-pointer, so there's no real room up here for work, so I'm going to do all my work down here. We'll determine the average velocity of the car from 6 seconds to 10 seconds. And if you just, and this one's really just interpreting the graph. We're going to look over here and we're going to see 6 seconds all the way to 10 seconds. The velocity isn't changing, it's this horizontal line. So the answer is just the 15 meters per second. That was a pretty straightforward one. No traps. I know when you're taking this test it probably felt like there was a trap here. You had to do more work, but nope, sometimes they are just gimmies. 64, we want to determine the car's acceleration during the first 6 seconds. Here's where it's important to remember your velocity time graph stuff. And if you remember, for a velocity time graph, the slope of a velocity time graph is indeed the acceleration. Now, so basically, we're just looking for the slope during the first 6 seconds. If you don't remember that, let's think about what the slope of any graph is. The slope of any graph is simply the rise over the run. In this case, it's the rise is the change in y, so it's the velocity divided by the time. So the slope is the change in velocity over the change in time. And if you look in your reference tables, that is A. So let's do that. Let's find the slope. Slope will equal the change in y. That's going to be 0 to 15, so we have a change of positive 15 meters per second over your time of 0 to 6 seconds. And that ends up being 2.5 meters per second squared. Units are already given, just got to toss in the number. And finally, 15, identify the physical quantity represented by the shaded area in the graph. We're not looking for a number here. We want you to tell us what this shaded area even means. What does it represent? It must mean something. It represents something. And the shaded area is indeed the area, which for a velocity time graph is displacement. And that's the answer. Area is displacement. We'd accept distance, and we'd even accept writing words like the car. This is how far the car traveled. So you didn't need to remember the word displacement. You could have written distance, and it would have been fine. How can you remember that? Well, look at it's the area of a graph. And let's just take a look at this area of this rectangle, because it's a nice, easy shape. That area is velocity times time. Well, average velocity times time is change in distance, which is displacement. All three of these were worth 1 point each. All right, I'm skipped pretty far ahead. I'm on went on with number 71, so the rest in the meantime so far has been content that we have not covered. This is a gravitation problem. We've got Pluto orbiting the Sun, and we know some information for the Sun and Pluto, etc. We have Charon, which is Pluto's moon, and then we have the mass and distance given. And so we want to calculate the magnitude of gravitational force of attraction that Pluto exerts. Well, this is going to be the universal gravitation equation. We do need to show our work in substitution with units. I think for this one I'm going to lead off with the equation so I can make sure I make my knowns list. And really, please, make your knowns list. It's going to help. These universal gravitation problems have extremely low percentage of kids that get all full credit, because they always leave out stuff, or they have silly little math calculator errors. So just be slow when you do this problem. Take your time. Make sure you get those 2 points. And so G is a constant. It's on the front page of your table of information. I'll go ahead and write that down right here. That's going to be 6.67 times 10 to the negative 11. And it's got units of Newton square meters per kilogram squared. We're going to need to know the mass of both Pluto and Charon. And it looks like they've been given it. Pluto has a mass of 1.31 by 10 to the 22. And Charon has a mass of 1.55 by 10 to the 21. And finally, we're going to need to know the distance between the two, because that's what pulls them through. And it shows you here, Charon orbits Pluto with their center separated by a distance of 1.6 by 10 to the 7 meters. That's the distance we're looking for. That's our R value. 1.96 times 10 to the 7 meters. Now, making a knowns list will allow us to ignore our units when we're writing it into this equation here. If you don't make that knowns list, there's a very good chance you forget to plug those units in, because there's a lot of stuff that you're writing down. I got to shrink this up. I didn't give myself enough room. Alright, so at this point it's just plugging in and solving. Pay attention though, don't forget that square into the by the R. It's going to come into play. So the answer we're looking for is 6.67 times 10 to the negative 11. You know, I'm going to do this work down here because I know I'm not going to have enough room. Oops. So let me just go ahead and start that over. On the actual test, you have significantly more space. I had to shrink this down for display purposes, so it's, anyhow, my work's down over here now, 6.67 times 10 to the negative 11 times 1.31 times 10 to the 22 times 1.55 by 10 to the 21. Oh. And all of this we're going to divide by the distance between them. We got to make sure we square that distance. When you put that in your calculator, it gets a little wonky. So I encourage you to use double parentheses. I encourage you to do 1.96 times 10 to the 7 in one set of parentheses. After you close that, raise that and square it, and then close that set. That way, this entire term, you're assuring that you're only squaring this bottom term. This is one that you really ought to practice. Right now, you should get your calculator out, and you should do this over and over again until you get it right. You're going to get a value of 3.53 times 10 to the 18 newtons. If you're not getting that number, you're not doing it right. Make sure you practice this. Alright, 73, 74, we want to know the magnitude of the acceleration of Charon towards Pluto. Well, at this point in time, you got to understand these forces are equal and opposite. So for 73 and 74, the force that is pulling Charon or the force that's pulling Pluto, whichever one you want to call it, it's going to be the same value. It's what you just found. So we do need to see here that the net force acting on anything is equal to mass times acceleration. Therefore, the acceleration acting on this object is the net force acting on it divided by its mass. Since we're looking at the magnitude of the acceleration of Charon towards Pluto, we've got to use Charon's mass, which is going to be, well, first we've got to use that force we just found, 3.53 by 10 to the 18. We're going to divide that by the mass of the planet, and please don't forget your units, even though you may have shown your units up top, it's a whole new set of problems, so you got to redo your list and remake your units. So we're going to divide this by the mass of Charon, which is going to be 1.55 by 10 to the 21 kilograms. And you will get a value, I better type this one on my calculator. You get a value of 2.28 times 10 to the negative 3. And it's acceleration, so it's a meter per second squared. Again, to get both points, you need to have units and knowns and substitution, the original equation, and really everything that you can think of. Just get it down there. Oops. Okay, that box is not. There we go. State the reason why the magnitude of the Sun's gravitational force on Pluto is greater than that of the magnitude of the Sun's gravitational force on Charon. What's the reason why the Sun is going to pull Pluto more? Well, the only factor that's really going to be different is going to be the mass. If you look at the mass of Pluto, it's a factor of 10 larger. Therefore, it is indeed going to have a greater pull towards the Sun. So pretty much, you got to use the word mass. Pluto has more mass. Don't say larger. Anyhow, don't say larger because larger doesn't necessarily imply mass. It could just mean more volume. So please, use the word Pluto has more mass. Alright, I'm going to go ahead and we're going to do number 76. 76 through 80 is given this information here, and we're dealing with a 20 Newton force being applied to a 5 kilogram box to push it across a rough horizontal floor at a nice constant velocity to the right. And we want to know the magnitude of the force of friction acting on the box first. There's no work here. What you have to show, not show, but understand, is that this is at constant velocity, which means we're in equilibrium. If I were to draw a free body diagram, any force that's to the right needs to have a net force to the left equal an opposite. We could have two forces to the left as long as they add up and equaling the same value to the force to the right. This example, there are only two forces in the x dimension. There's the push that's causing it to go to the right, and then you've got the impeding force of friction, so they have to equal each other. So the answer 76 is the same value as the horizontal force, or 20 newtons. They have to equal. Let me go ahead and finish that free body diagram, though, just in case I need it in the future. I know I have a normal force up because of the ground, and I have weight down the weight of the box. Okay, 77 through 78, we want to determine the weight of the box. Well, the weight of all objects will equal mass times gravity. So it's the mass of the box, 5 kilograms. Please include units or make a knowns list. Times acceleration due to gravity, 9.81 meter per second squared. Again, include your units or make a knowns list, and you will get a value of 49 newtons. And I am just making all kinds of extra dots here wherever I put my hand. 78, we want to determine or 79, we want to determine the coefficient of kinetic friction between the box and the floor. Well, since we know the force of friction, we can now go ahead and use the equation. Force of friction is mu Fn, or n, and we're looking for the coefficient of friction, so mu is what I'm looking for. Mu will be the force of friction divided by the normal force. Well, if you pay attention to my free body diagram I drew earlier, we'd see here that the normal force and the weight have to equal each other. So I actually know the normal force. It is the 49 newtons. So it's really just to be 20 newtons divided by 49 newtons. And let me calculate this. We get a value of 0.41, and it's unitless because it's a coefficient, so no unit. Alright. Looks like that's it for the 2014 exam for everything that's covered in the mechanics world.